In this example, we're asked to determine whether or not it's possible that this vector field, this given vector field, is actually the gradient of some function little f. And if so, we want to find the function little f. So can we find this function? That's the question. Can we find a function little f for which this is a gradient? So let's start by remembering what it means to be a gradient. And of course, gradient vector field, this is one we're familiar with. This is just a function whose component functions, so components of the vector field, are the partial derivatives of the original function. Okay, and so if this is going to equal f, then what we end up with is actually a system of equations. So I'm going to just write this out, and then we can look at the system of equations that we get. But this is our question, right? Is it possible to find a function whose gradient field is equal to this given vector field? And so if it is possible, then what has to be true? Well, the x derivative of our function has to equal all this, and the y derivative of our function has to equal this. So we get two equations then. The first one says that d by dx of f, I'm going to write it this way because it's suggestive, okay, this should equal this whole function here. So 3y sine of x plus 3xy cosine of x. And then similarly, the y derivative of our function, d by dy of f, this should equal just 3x sine of x. And if these two things are true, then what we can do is we can try to eliminate these derivatives by integrating with respect to the appropriate variable. So if we want to take away the x derivative, we have to integrate this whole thing with respect to x. Same thing with this one. If we want to get rid of the y derivative, we have to integrate this one with respect to y. And then once we've done these two things, we have to ask, is it possible that these are equal? These two integrals are equal to each other? If so, then we'll get back our function f, right? Because in both cases, if we integrate out the x partial derivative of x, we end up with f, right? With just f by the fundamental theorem of calculus. Same thing here. If we integrate out the y partial derivative with respect to y, we get back f. Well, of course, f should be equal to f, right? It should be the same function. So let's do these two integrals and see how it works. These are partial integrals, so we should be okay with this, but let's compute them. So I'm going to copy this one and start with this. And let's do this one first. All right, this one is an integral, obviously, that has two separate parts, so I'm going to break it up. So the first one is 3 times y, times sine, I'm doing the integral already, times sine of x dx, plus the next one is going to be 3 times y integral of, this is going to be x times cosine x dx. Okay, I've taken out the constants, and remember, with respect to, when an integral is with respect to x, the y variables are treated like constants in this situation, right? So the first one can just be computed. This one, the integral of sine is minus cosine, so this is just minus 3y cosine of x. Okay, then there's a plus c. We'll deal with that at the end. This one needs to be done by parts. Okay, so when we do this by parts, we can make our little table of u and then dv. So this is going to be cosine x. Integral of cosine is sine of x. Integral of sine is minus cosine of x. And then we know that this process goes kind of back and forth like this. And so when the slope is down from left to right, it's plus, and then minus this way, which is kind of opposite what we're used to, but we know how to integrate by parts. So this is then plus x sine of x, but there's a 3y here, right? So 3xy sine of x, and then minus a negative. So this is also plus. This one is going to be 3y cosine of x. And at this point, I have really not planned out my work well, so I don't have room here. I need to add plus c, right? But before I do so, notice that this one and this one are going to cancel out, right? And so what we end up with is that this integral is equal to 3xy sine of x plus c. But this integral was only with respect to the x variable. It wasn't with respect to y. So it's possible that this c, I'm going to call it c1, this c could actually have y's in it. It could be a function of y. Okay? It can't have x's because the integral would have seen it. It would have found it if it had x's. But if this is a function of, say, y squared or something, the integral wouldn't see that. Okay? So the integral wouldn't find that, and we have to account for that. All right, the other integral that we have to do now, so this is a potential answer for our function f, but we need to make sure that it obeys this integral as well, right? And so the other integral we have to compute is 3x sine of x dy, and this one is going to be much breezier. So 3x sine of x dy. This whole integrand is a constant with respect to y. So when we integrate this with respect to y, it just multiplies by y, right? So this will be 3xy. I'll put it in there just because we know where it's headed, right? But we should, before we jump to any conclusions, we should notice that this integral, again, same scenario, is only with respect to y. So there is potential that this integral could miss not only constants, but functions involving x, right? Could miss functions involving x. And so now we get that this integral is 3xy sine of x plus c2 of x. And here's the kick, right? So this should equal f, and this should equal f, if it's possible to find our f. And we notice that we've got one part of this, but two copies of this that are the same. Okay? Then we've got these unknown constants, which we say, all right, this one could depend on y, this one could depend on x. They have to be equal, though, whatever these two are. And so let's just, in other words, they have to just be a constant, because there's no way that x can equal y. Okay, but let's just say we were only asked to find, if we go back to the question, to find a function that satisfies this, and find 1, right? So let's choose the one for which this constant is equal to 0. And what we've done then is we've found that this function, f of xy, just by integrating a couple times and comparing our answers, f of xy equals 3xy times sine of x, this function satisfies this property that its gradient, the gradient of this function, is equal to the original vector field that we were given. Okay? And so this idea is going to come back very soon and throughout the rest of the semester, this idea of finding a function whose gradient is equal to a given vector field. And this idea is extremely, extremely important. And these functions are called potential functions of the vector fields. So we'll see these a lot moving forward.